After completing this chapter, you will be able to define the terms center of area, center of buoyancy, and center of gravity. Recognize how a righting moment is created and how its value can be calculated. Identify the effect on the ship's center of gravity caused by adding, moving, or removing mass. Use a table of moments to find a resultant center of gravity for a ship. The center of area of a plane surface is the geometric center of that area. The center of gravity of an object is the point through which all the mass of material in that object can be considered to act downwards due to the Earth's acceleration due to gravity. The center of gravity is the point about which the object could be steadily balanced. If we consider the fact that every action creates an equal and opposite reaction, as defined in Newton's laws, there must be equal forces acting upwards at this same point of balance. When considering a floating vessel, the upthrusts are known as the forces of buoyancy. They act over the complete underwater volume of the ship and increase with depth. But the total force of buoyancy can also be considered to act at its centroid, the center of buoyancy. The center of buoyancy, B, is at the geometric center of the underwater volume. When these forces upward, buoyancy, and downward, weight, are in a steady state and are acting through the same vertical line, they are referred to as being in equilibrium. On a ship, the weight of displacement acts downwards at the center of gravity, and the force of buoyancy acts upwards at the center of buoyancy. When the vessel is in equilibrium, these two centroids will be in the same vertical line and of the same magnitude. A ship is in equilibrium when the weight forces acting downwards through the center of gravity G and the buoyancy force acting upwards through the center of buoyancy B are in the same vertical line and are of the same magnitude. When a vessel is heeled over by a wave, G remains on the center line, but the center of buoyancy moves off the center line to the new geometric center of the underwater volume. Since G and B are no longer acting in the same line, there will be a righting moment of displacement times their distance apart, trying to bring them back into the same vertical line and to return the ship to the upright equilibrium position. The perpendicular distance between the ship's center of gravity, G, and the vertical upthrust through the ship's center of buoyancy, B, is known as the righting lever, and given the value Gz. This is the lever that is created when B and G are not in the same vertical line, and provides the righting moment to return the vessel upright after being inclined over by an external force, such as a wave. The value of this lever is plotted as the y-axis in a graph known as the curve of statical stability. This will be discussed later in the course. As described previously, the moment of a force is a measure of the turning effect, and when considering the righting lever Gz and the force of the displacement, this righting moment is known as the moment of statical stability. Units ton-meter. When a weight is shifted on board, loaded onto, or discharged from a ship, the original center of gravity of the ship will move parallel to a shifted weight, directly towards the loaded weight, directly away from the discharged weight. On a ship working cargo, this will normally result in the center of gravity G moving at an angle from the center line. To make this easier to calculate, the movement is normally broken down into two parts, the horizontal movement and the vertical movement. A weight already on board is lifted from the deck using the ship's derrick, which is plumbed directly over the weight. As the weight is lifted off the deck, the centre of gravity of the weight will instantly move vertically upwards to act at the point of suspension, the derrick head, and the centre of gravity of the ship, G, will move accordingly. The vertical distance, D, moved by the centre of gravity, G, of the lifted weight, will obviously be large, deck to derrick head, and the vertical shift of the ship's centre of gravity, G, will move a large distance accordingly. This can be calculated by the following formula. GG1 is equal to W multiplied by D divided by displacement. A ship is loading a weight from the quay using its own crane or derrick. The ship's centre of gravity will follow the movements of this loaded weight during the various stages of loading. It will move upwards and outwards towards the derrick head during the initial lifting off the quay, back parallel to the swinging derrick head, and finally upwards and outwards from its original position towards where the weight is eventually placed on the deck. The final position of G would obviously be different to its original position before loading, and the overall displacement would have increased by this added weight. The above formula should be repeated 4 times to determine the various positions of G during the loading process. Vertical movement of G when the weight is suspended by the derrick over the quay, where D is the vertical distance from G to the derrick head. Horizontal movement of G, where D is the horizontal distance from G to the derrick head over the quay. Horizontal movement of G when the derrick swings the weight from quayside over to the final position of the weight on the deck, and D is the distance moved by the derrick head. Vertical movement of G when landed on the deck, where D is the vertical distance from G to the G of the weight on the deck. When a single weight is loaded, discharged, or shifted, the new G can normally be obtained in a single calculation by taking moments about the original centre of gravity, G, as shown previously. However, when a series of weights are loaded at different positions on the vessel, the most effective method of calculating the new centre of gravity is to use a table of moments. When the transverse centre of gravity is required, it would normally be calculated by taking moments of all the weights about the keel. If it is the longitudinal centre of gravity that is required, it would be calculated by taking longitudinal moments about a point such as the after perpendicular. The total vertical moments would be the sum of each weight multiplied by its distance from the keel, and the result would provide the position of the ship's centre of gravity from the same reference, the keel. We have now reached the end of this chapter about centroids. We have learned that the centre of buoyancy is at the geometric centre of the underwater volume, whilst the centre of gravity is the point through which the weight of the body acts. The centre of area of a plane surface is the geometric centre of that area. If the centre of buoyancy and the centre of gravity are not in the same vertical line, then a righting moment is created, with the righting lever GZ being the perpendicular distance between the lines of action of the weight and the upthrust. The centre of gravity of the ship changes with the loading condition. The centre of gravity moves towards a loaded weight, away from a discharged weight, and parallel to a shifted weight. The centre of gravity of a lifted weight moves to the head of the derrick as soon as the weight is lifted from the deck. The resultant position of the centre of gravity, kg, can be found by using a table of moments and dividing the total moment by the final displacement.